chemistry, we're on to lesson 11 on a concept known as ionization energy. So previously we said that similar charges repel and different charges attract each other. These are referred to as Coulomb forces. So Coulombs Law states that the electrical force, the force between two charged particles, either a proton and an electron or two electrons or two protons, is given by the formula electrical force, that's F sub E, equals a constant called Coulomb's constant, times the charge on the first particle, that's Q1, times the charge on the second particle, that's Q2, over the distance between those two particles squared. Now, I'm not going to ask you to work problems with this formula, but you should just understand that that's the formula for basically what we're going to talk about all semester in this course, which is the force between the force that attracts an electron to a proton or that repels two electrons from each other. It's given by this formula. So there we go. That's what we're referring to as that repulsive attractive force that exists between particles. Almost everything that happens in chemistry is the result of Coulomb forces. So Z number. Lithium has an atomic number of 3. That means it has 3 protons. The atomic number is the number of protons. The atomic number is also called the Z number. The atomic number is the number of protons in an atom of an element. So here we see lithium, and it has 3 protons, and if it's electrically neutral, it has 6 protons, 6 electrons. Then this lithium, this is the most common isotope of lithium, it has 4 neutrons. Overall, lithium has an atomic mass of 6.94. That means that there are some lithium atoms that only have 3 neutrons. So if you average the lithiums that have a mass number of 6 with the ones that have a mass number of 7, you end up with a number that's pretty close to 7. That's the most common isotope, is the 3 neutrons. Again, this is just a little bit of extra review here. All right, so the core electrons are electrons inside of the valence orbital. The core electrons are said to screen or shield, those two words can be used interchangeably, the valence electron or electrons from the pull of the protons in the nucleus. So there again you see the lithium atom. Core electrons are all electrons inside of the valence orbital. These electrons screen the valence electron from the pull of the protons. So in the case of lithium, lithium has 2 orbitals, and so the valence orbital is the second orbital. That simply means it's the outermost orbital, and that one electron out there is called the valence electron. So any electrons that are between the valence electron or electrons and the nucleus are said to screen, are called core electrons, and they're said to screen the valence electron. In other words, if you look at that valence electron, you can see it's not going to feel the pull of the 3 protons as well as it would if those 2 core electrons were not there. They're kind of blocking it. They're like clouds on a cloudy day that keep you from seeing the sun. And they're kind of blocking the ability of that valence electron to feel the pull of those 3 protons. Therefore, the valence electron is not going to feel pulled quite as tightly or as tightly as it would if those 2 core electrons were not there. Valence electrons are electrons in the outer orbital, so that one right there. The effective Z number, and that's the symbol for that is Z with a subscript of EFF. Z effective measures how much the pull of the protons that an electron feels. So the Z effective number equals the Z number. Now the Z number is the number of protons, that's 3, minus the number of core electrons. So in this case you see that there are 2 core electrons. So for the valence electron of lithium, the Z effective would be 3, the number of protons, the Z number, minus those 2 core electrons, which equals 1. So in other words, what that means is this. Although lithium has 3 protons pulling on its electrons, its valence electron feels the effective pull of only 1 proton. So it's not feeling pulled as tightly to the nucleus as, say, the 2 core electrons, or as it would if those 2 core electrons weren't there. So the core electrons are doing 2 things. They're blocking the pull of the protons on the valence electron, and they're also repelling the valence electron. They're pushing it away. They're pushing it out. So it has 2 effects. And so it's a simple equation. It's an approximation, but it's pretty accurate, that this lithium, even though it has 3 protons pulling on the valence electron, it doesn't feel 3 protons. It only feels the pull of 1 proton. 3 minus 2 equals 1. So there you see right there that if we basically made those 2 core electrons disappear, but we also made 2 of the protons disappear, so that's effectively, those 2 canceled out. The 2 protons, 2 core electrons canceled each other out in effect, and now that electron only feels the pull of 1 proton. So this is a key concept, ionization energy. You're going to hear this term probably almost every day or 3 times a week in this class. Ionization energy is the amount of energy that's required to pull an electron away from its atom. And this is important because when an electron gets pulled away from an atom, and it could be more than 1 electron, then that atom becomes charged. It becomes a charged atom. It has a positive charge because it has more protons than electrons. When it becomes positively charged, it can be attracted to other atoms that are negatively charged, or to other particles that are negatively charged. So ionization energy is the amount of energy that is required to pull an electron away from its atom. So the man represents ionization energy. The ionization energy must have greater pull on the electron than the protons do. So there goes the electron, it gets pulled away. Ionization energy is also called electron binding energy. Really, that's the case when you're dealing with metals, and ionization energy usually refers to gases. But in this case, in this class, we really only use the term ionization energy. So ionization energy increases as you go from left to right across the periodic table, and it increases as you go from bottom to top up the periodic table. So ionization energies increase up a group being a column, and right in a period, that is across a row. So that means the highest ionization energies are in the upper right-hand corner of the periodic table. So if you look at some of the elements up there, would be oxygen, fluorine, neon, helium. Those have very high ionization energies, meaning that it's very difficult, almost impossible, to pull an electron away from them. It takes so much energy that it will pretty much never happen. So here's a perspective view of it. Ionization energy is greatest in the upper right-hand corner of the periodic table where helium is. So you can see helium is the tallest of those blocks. That's the highest ionization energy. The lowest ionization energies are going to be down where you see cesium, barium, rubidium, strontium down in the lower left-hand corner. Those would be the lowest. The highest would be, as we said, helium, neon, so forth, up in the upper right-hand corner. So ionization energies are lowest when an electron is furthest away from the nucleus, has more orbitals. So let's look over on the right-hand side. You see just a section of the periodic table there. You see the second row, and you see the second to last column. That would be the halogens, fluorine, chlorine, bromine. So if you look there, the images are not real sharp, but if you see bromine down there in the bottom right, and up above you see fluorine, you can see that bromine has a lot of orbitals because it's down in the fourth row. And so that means that its valence electrons are way out in the fourth orbital. They're a long way from the nucleus, and so it's easier to pull them away. You also notice that it has a lot of screening electrons. or shielding electrons. Remember, screening or shielding electrons are the ones that are inside, any electrons that are inside the valence orbital. So that would be the first, second, and third orbitals for bromine. Those are shielding the valence electrons from feeling the pull of the protons in the nucleus. So bromine, it's much easier to pull the valence electrons away from it than chlorine up above. If you look at chlorine, it only has 2 orbitals. So its valence electrons are closer to the nucleus. Now, yes, fluorine does have a lot fewer protons than bromine, but still, the fact that there's so few orbitals and so few shielding electrons blocking out the valence electrons from feeling the pull of the protons means that fluorine has a very high ionization energy. So let's read this again. Ionization energies are lowest when an electron is furthest away from the nucleus, has more orbitals, and the nucleus has fewer protons. So we addressed that in the column there, even though fluorine has fewer protons, that's not the most significant factor. The most significant factor is that it has fewer orbitals and that the valence electrons are closer to the nucleus. Now let's look at from left to right. Over on the left you see lithium. And lithium has 2 orbitals just as fluorine does. But lithium has only 3 protons to pull in on the electrons, whereas fluorine has 9. So the effect of the protons dominates there and means that fluorine will have a higher ionization energy than lithium. Again, ionization energy means how much energy does it take to steal an electron away from an atom. Fluorine is one of the hardest, okay, because it has few orbitals and fewer orbitals than bromine down on the bottom, but it has more protons than lithium over on the left. So let's read this. So lithium has a lower ionization energy for its valence electron than fluorine because its valence electron is the same distance from the nucleus as fluorine's electrons, that is 2 orbitals. They're both out 2 orbitals, but it has only 3 protons to attract him, while fluorine has 9 protons to attract its electrons, its valence electrons. So the Z effective of lithium is 1. The Z effective of fluorine is 9. Let's think about it. It has 9 protons, and just like lithium, it only has 2 core electrons, those 2 first orbital electrons. It doesn't matter that fluorine has a lot more electrons in the second orbital. They're not blocking each other. They're not in each other's way. They're all side by side. So you can see that the Z effective for fluorine is much higher than the Z effective for lithium, and that means fluorine will pull in on its valence electrons much more strongly than lithium will. Bromine has a lower ionization energy for its valence electrons than fluorine because it has more orbitals. So its valence electrons are farther away from the nucleus, what we said at the beginning here. So let's summarize that. When you go across a row or a period, the dominant factor is number of protons. You increase the number of protons as you go across the second row from lithium to fluorine, so fluorine has a higher ionization energy. As you go up or down a column, the dominant factor is orbitals. Yes, bromine has more protons than fluorine, but that's not the dominant factor going up and down a column or a group. It's the number of orbitals. That's what dominates. So even though bromine has more protons, it's still, because it has more orbitals, it's easier to pull the electrons away from bromine than it is to pull the electrons away from lithium. Each electron in an atom has its own ionization energy. These are called first ionization energy for the first electron ionized, and the second ionization energy for the second electron, and so forth. The valence electron of lithium has the lowest ionization energy. Of the 3 electrons that lithium has, the valence electron has the lowest. It's the easiest to pull away because it's shielded from the nucleus and has a Z effective number of 1. So there it goes. Now once it goes away, we just kind of assume that the second orbital disappears. It's still there, but it's not being used. So we're now going to say that once lithium is ionized, it now has 1 orbital, and that one orbital has 2 electrons in it. The first ionization energy of lithium is 520.2 kilojoules per mole. Now that's kind of a new concept. Just understand that's an amount of energy per number of atoms that you have, okay? Kilojoules per mole. We'll get into those units of measure later. So 520, just remember the number. Note that the units kilojoules per mole are a measure of energy that we will discuss later. Each electron in an atom has its own ionization energy. These are called the first ionization energy for the first electron ionized, the second ionization energy for the second electron, and so forth. The second electron of lithium has a much higher ionization energy. It is not shielded from the nucleus and feels the pull of all 3 protons. So its Z effective number is 3. There are nothing shielding those last 2 electrons from the nucleus, so they both feel the pull of all 3 protons in the nucleus. So there goes the second one. So the second ionization for lithium is 7,298.1. So much higher. About 13 or 14 times higher than the first ionization energy. So again, same thing that it said on the previous slides. So the last electron of lithium has the highest ionization energy. It is not shielded from the nucleus and feels the pull of all 3 protons. In addition, it does not feel repelled by the other first orbital electron. Those 2 first orbital electrons were slightly repelling each other, and that made them have lower ionization energy. So once that other first orbital electron went off, then that last final electron that you see there doesn't have the repulsion of the other electron, and so it's held even more tightly to the nucleus by the 3 protons. So in addition, it does not feel repelled by the other first orbital electron, which has been removed. So the Z effective is 3, but it also doesn't have that other electron near it. So it's gone. So the third ionization energy for lithium is 11,815. So it's much higher than even the second ionization energy. And that takes care of our lesson on ionization energy. So just to repeat, ionization energy is the amount of energy it takes to pull an electron away from its atom. And that will become a very important number as we study further in chemistry.